Hello. You're back. Hold on. Let me pull up the chat here. Hold on. I don't know why I forgot to do this. I was like all ready and everything, and it's just like this is the one thing that I actually forgot to do was this. Now I gotta waste a little bit of time doing that. Ain't that fun? All right, all right, all right. In we go. Cool. Chat is now open. Nice. Okay, what are we doing today? We're set theory gaming. We are gaming. So yeah, last time we did combination world, which I think was just like combine all the things you know and start just proving stuff. They said they were going to be a little bit more hands off with it, so I think yeah, this one looks like it's a little bit more on the tricky side. So yeah, what were we doing? Actually, let's look at number 1. Okay, what did we do for number 1? Right, and that was like this X thing. What does X do? It's been a while. It's been exactly 1 week. If your goal is A equals B, when they're both sets, you can X to introduce a new arbitrary object X into the proof. There was like another thing they said you could do. You don't have to use X. I don't remember what it was. We got. There's also like push neg. Your goal is a negative statement. Tactic push has to be expressed as they call it positive. Oh right, this is like the double negation elimination. Alright, we know what exact does. What was the alternate thing to X? I honestly just don't remember. Was it constructor? No, this is for if and only if. Ruh-roh, okay. Well, hopefully I will remember at some point, or someone can remind me. If JC Pie shows up or something, maybe. Maybe I can actually remember this. Alright, if, no, of course, you could start the proof in this level with either X or apply subset on entity. Okay, never mind. They just straight up tell me. Okay, I don't need to actually jump through those hoops. But there's a shorter solution. You can use the theorem from the previous level, compl union, to prove the theorem in this level. Oh, okay. So this is building off of the last level. What was compl union? For any sets A and B, compl union AB is a proof of the statement A union B's complement equals A's complement intersect B's complement. Right. This is almost like De Morgan's law sort of thing. Actually, it kind of just is, isn't it? Yeah, this is kind of just De Morgan's law, but on sets. Compl union to prove the theorem in this level. Okay. They do look pretty similar. Yeah, this is also like a like different form of that same De Morgan's law. Compl union. The trick to get started on this proof is to rewrite this boy as this boy. Okay. How am I going to do that? As you know, compl is a proof of the theorem. Okay, so we need to rewrite compl for that. We want to go in the opposite direction, rewriting the union as this. Oh, so we'd use the left arrow. Right, okay. Let's just take a look at compl again, just to be like absolutely sure we know what we're doing here. Right, this is basically the double negation rule, but on sets. Yeah, okay, I see. How do you type? Is it this? No, shoot. Okay, it's compl. Union? Okay, yeah. I mean, these are the kinds of things that you kind of have to get used to. You see how you can now use the theorem from the previous level. Let's see. So we have compl union. That's saying that A union B's complement. Okay, so that would be like this guy. Yeah. So complement of this, where A and B are replaced with A complement, B complement. We should be able to convert that to the intersection. There we go. And then we just use compl again. So where's compl? Yeah, so this should be super simple. Oops, don't type that. Compl, there we go. And then it should just be like REFL. Do I even need to use exact here? No, okay. Cool, good start. This proof is longer than previous ones, but it doesn't require any new tactics or theorems. Just stick with it, keep applying the ideas from previous levels. Once again, Lean has left out some parentheses that it regards as unnecessary. It gives intersection higher precedence than union. Okay, that's good to know. So they prioritize and over or. So it'll interpret this as A and B, union A and C. Okay. I have to figure this stuff out for my own little programming language I've been working on. So it's kind of good to see like how they're making their choices. Anyhow, what are we doing? So we got A intersect B union C equals A intersect B union with A intersect C. So this is like distributivity. All right. So we're starting with an equality. Do they want me to use like stuff that I've used before though? We have compl inter now. Like, does this show up anywhere usefully? Well, we don't really have any compls yet, so I guess we can't apply this. Same. Well, we could maybe use this to introduce some compls, I guess. What is this one? Yeah, some of these are kind of complicated. Well, we're not dealing with subsets right now, so that's fine. This one might be useful at some point. But I think, yeah, this one probably isn't using any special tricks. Let's just use X. So if we open with an X, let's see what that does. Because I think what this does is it uses a new arbitrary object X into the proof. And sets the goal to be one of these. Right, okay. I don't know, this is looking a little bit complicated though. Right. We're okay. So we might end up descending into the level of using subsets anyway. Okay. Well, we have an if and only if. Let's just break that down. I don't have an assumption like that. Right, apply if intro. Break these down into two goals. Okay. I think that's a good start. So we have x is an element of all of this. Implies that x is an element of all of this. That's a lot of stuff. Let's see. What are we gonna do? So we got these. So you're a union on this side. You're this on this side. I should probably start by turning the implication into something else. So if my goal is this, I can use intro. Yeah, we're gonna just do that. Yeah, that looks a little bit more reasonable. Okay, so what is all this? Okay, this is interesting. Mem enter if. I guess I could break this down further then. This is looking like an interesting... Right, and I can use this as a rewrite rule if I want. I probably will. So mem enter if is looking pretty good. That was pretty juicy. We don't really have a union here. This is the top level. So no, probably not mem union. No subsets yet. All right, we got associativity at some point, but we don't have a second union, or sorry, a second intersect. That's just swapping the order. It's not really important. Yeah, this is associativity for unions. Yeah, mem enter if is looking probably ideal here. Let's just open with that. Mem enter if. Oh, is that not going to work? Oh, at h. Okay, so now we've rewritten the hypothesis. So we now have a pair. We have x is an element of A and x is an element of B or C, or B union C, rather. Okay. So if I had an or, I could break that down. Okay, we don't have like anything else really. See what we can do. I don't know, I feel like I need to rewrite the goal a bunch. Is there a way I can like turn this into sub goals? Because I have this x as an element of a here, which seems kind of good for dealing with these a's. That's what I want to do. So what can I do with unions? What does constructor do again? No, that's not what I have. We don't have an or here, so I can't use this. Let's see. No, I don't think that's useful here. This is looking kind of juicy, I'm not gonna lie. We don't have any complements here, but I think we might want to introduce some just so that we can flip some signs around. It's definitely looking kind of tricky though. Because I don't have... Yeah, I have mem inter if. I don't have like a mem... I have mem union though, actually. You know, I actually do have mem union. Hold on. I actually forgot about this one. Okay, so if I use rewrite mem union, that seems pretty good. Get that on the goal. Okay, so now it's given me the show more help. So I think I've made some progress. I think I've made good progress if it's gonna be doing that. So we gotta break down the or now. Right, we don't have A and B. Should I R cases this? No, I don't have a proof of that. Okay, we're gonna just go left here. Actually, well, which one do I think I can prove? I feel like both of these are equally doable, I guess. So I guess we'll just start with left. The hint thing went away. That's interesting. Did I go down the wrong road? So if A is in the intersection of A and B, this is what our goal. So we want to prove that X, yes, is in the little subset between A and B. We know that X is in A. But this says X is in B or C, basically. It's in the union of B and C, which is not good, because we want to... We want to prove that it's in this intersection of A and B. So, like, if it's in C and not in B, then we can't prove this. But the same thing would be true if I picked the right-hand side. Because then it would just be like A intersect C. And then we have the same problem with B. I don't know if I wanted to go left here. I think I need to process my H a little bit more. I think that's what the problem is. Maybe I need to do something about you, because we have this union sitting here. I could break this one down with mem union, I guess. I mean, we can do this, if that's helpful. But no, the problem still is you. I don't know if we wanted to do this left. I'm gonna be honest. I think we didn't want to do that. I think that was a mistake. I think I messed up when I did that. I think I'm gonna do a double rewrite. Just break it all down to ands and ors. Okay, I think I need to do something with you. Like, I need to split this up. We need to break up the band. And I think the way I'm going to do that is with have, probably. So we're just going to be like, have L is H dot left. And then we're going to have R H dot right. It's probably unnecessary. And then we can like R cases this. Am I right? I'm right? R cases R with H1. Okay, so now we should be able to and intro these two guys, right? I know this is not like the sexiest proof ever, but I think it's gonna work. So we want to do like a, what was it? Or.inl. Okay, that's looking good. Now we have the same thing, but on this side. So yeah, I didn't want to do that left earlier. That was a mistake. So thankfully I course corrected. Yeah, shouldn't I just like copy this, but just put, I guess, instead of in else in R, do R. Actually, wait, is it? Sorry, what is my left and right? No, we still need L. This H2 goes here. Okay, cool. We are done half of the proof. So the other half comes in here. We have another hypothetical. Let's start with, I always forget this. We need to do an intro H. So we break that guy down. Then we basically just need to do the same thing that we just did, I think. Which was just like a shit ton of rewrites. Alright, we're gonna just rewrite mem enter if at h. I shouldn't just like randomly guess. I should actually probably look at it. Right, so we can rewrite the goal into this form. Let's just do that. And probably mem union. Right? Yeah. See, like, this is working. This is working for me. This, I can deal with this. And then we do a bunch of rewrites on the hypothesis. So your union. So we're going to have to do a mem union first at H. Here we go. Then we're going to rewrite mem enter if at H. And then we're going to do it again. Again, not the sexiest proof you've ever seen, but if it works, it works. We're going to take it. Okay, so we got to do an our cases here on our H, I think. Oh god, what does that look like? Our case is H with H1, H2. Sure. Yeah, that's looking nicer. Gives us another goal as well. So we got A and B. I can satisfy the left side of the goal pretty easily. Is there a way I can break down my goal, actually? Let me do that. So if I have an and in my goal, I can do an and.intro. Okay, that's just telling me how to deal with this. I guess we could just do the and intro. Yeah. So we'll do and.intro. We're going to take what's the left side of this? Logic. Wait, isn't there a way I can break this? I should be able to break this down, right? Wait, no, there was a thing in the... What am I doing? Yeah, if you have an assumption, h dot left. Okay. So h1 dot left proves that side. I guess I don't need these parentheses here, but I don't know. H dot right, except we need to do something with it. We need to make it an or. Or dot in L. So we're gonna just do this. Okay, that's looking pretty good. Now we only have one goal. So we just do the same thing. Except, actually, wait, yeah, isn't this the same thing? No, because we need to do or in R. No? Why do you not like this? I only had one goal left. Oh, because it's H2. My bad. There we go. Phew. Didn't use any hints. GG's. This is different from the previous theorem. The roles of union and intersection have been swapped. Once again, there is a tricky shortcut. There's a way to use the theorem from the previous level to prove this theorem. But if you don't see the shortcut, you can use the straightforward approach. If you made it through the last one, you can do this one too. Okay. Ooh, what is the trick? I kind of want to know what the trick is. So we have inter distrib left. This probably uses like compl, like compl. If I had to guess. We're probably gonna have to like invert something and then apply this. Right, because this one has union center. Yeah, these are basically it just flipped all of the signs. This feels very compl coded. I'm not gonna lie. What was compl union? We also have this compl union. We can also maybe use this, but we don't. We need to introduce the compls first. So yeah, I think we have to compl from right to left probably. I might have to target something in particular. Let's see. Wait, so we gotta do reverse. We do a reverse compl. I guess it wants me to actually target something. Makes sense. I guess we could do A union B inter C. Then we get this. Then we can probably use like compl inter or something. No, is there a compl union? We have compl union. I'm gonna go compl union. Oh, what the hell? Hi. You might be tempted to use rewrite compl inter as your next step, but in this situation, rewrite compl inter is ambiguous. because there are two ways that the theorem complement could be applied to rewrite the goal. Complement BC is a proof of B intersects C's complement equals B's complement union C's complement. And complement A complement B union C, or B intersects C's complement is a proof of A complement intersect B intersect C's complement. Okay. Equals A double complement union B intersect C double complement. And either one of those equations could be used to rewrite the goal. I'm sorry, you just kind of like spat a whole bunch of words out at me, and I have like no idea what you're saying. If you say rewrite compl then Lean will pick one of those two rewriting steps. It might not pick up the one you wanted, so you'd better say explicitly what you want Lean to apply the theorem compl to. Okay. So they're straight up telling me I'm probably gonna want to use compl here. Why is that? Right, they're telling me that there's two ways. I don't think I want number 2. The reason why I don't want number 2 is because that's basically the form that we started with. We wanted to flip the signs around, right? So like we want the first one. So if I rewrite compl I'm guessing it's gonna pick the wrong one. Let's see what that does. Yeah, it's just gonna reflip the sign. That's what they were saying. So if we do BC instead, then we get what we want. There we go. That's looking good. And now we need to just apply this guy, this bad boy. Because we have the A intersect and we have the B union C on this side. Oops. Whoa, why is it freezing? That's weird. Inner distrib lift left. Okay, that's looking better. So now I need to probably... well, all the signs are flipped. I need to convert U back into an intersect. So I think we're going to do that using compl... Was it compl inter or compl union? It's compl union. So we can compl union here. Oh, did we get more text or no? It's just re-scrolling to tell me what to... It's reiterating that last message. Intersect B complement. Okay, so we want to flip this guy and this guy. Those should be compl inters. I mean, this looks pretty compl intercoded. Okay, that guy's flipped. What about the other guy? There we go. That one I didn't have to target. And at this point, we just need to rewrite everything using compl again. All right, cool. Hey, let's go. Reflexivity. One more tricky theorem. Oh boy. This proof is a bit tricky, but you should know how to get started. All right, if you insist. So this is a goal that is a subset. Okay, we haven't touched a subset in a little bit. Okay. Don't think we're using anti-sim here. Oh. Okay, then what do I need to do here? I don't know if we can break down this subset actually. Now I'm looking at this. Doesn't look like that. What are we proving here? Example? Okay, suppose A union C is a subset of B union C, and A intersect C is a subset of B intersect C. Then A is a subset of B. Oh. Okay, this looks like a nightmare. This looks like a hell of a nightmare. Okay. That is not useful. Is this useful? Maybe. But probably not at this moment. Because this is just transitivity. Nah, I don't think it is. This is like bidirectional. Okay, yeah, no, that's not. You should know how to start this by now, bro. It's been it's been a week. So wasn't this a function? Or something like that. I seem to recall like either this or like this was treated like a function. Like you could apply subset. Okay, no, that's all you have to say about that. That's not helpful. Nope. Nope. That's for negations. Oh boy. So from this, we want to prove that A is a subset of B. Yeah, we don't have anything else. Does this help? There's no intersect here to play with. Like I have this A union C. So yeah, A union C is a subset of B union C. And A intersect C is a subset of B intersect C. It almost feels like we might be able to do something with transitivity at some point. but I don't know. Okay, hold on. I need to I need to go back and look at how subsets work. So what does this say? Right, this was elements. Teaching me exact. Right. We can apply this using exact. Or actually, we don't even need to use apply explicitly. We can just go like h1, h2. So if we have x element of A, and we have A to B, then we get x element of B. Okay, good to know. I think that's all I really need to know. You know what I mean? Like, I feel like that's the important part here. I hope I am right about that. So, I guess first we might want to break down the union. Yeah, mem union seems like it could be pretty good here, actually. We don't have an if and only if, though. Or I mean, like, I guess we wouldn't have one, but like, we have to break it into this form first. We need an element. So if I had an A union C from this, I could, I guess, apply this to that and get a B union C. Not that I necessarily want that. So how would we get membership from here, though? That's the question. I don't think we have access to that. I mean, we might just need to use this. I kind of forgot about this one, memcompl if. But no, I don't have this element right here. That's kind of the problem. So I need to remember how I did some of this stuff earlier. I don't know if we were playing with that. All right, use X. That only works if you have equality, though. Yeah, if you're not using equality, you don't have the ability to extract that into that. Okay, so maybe I don't want to do that then. Because like this works with x to x. This one was just, well, I didn't do that, right? This one was just fiddling with it. Using complements. Okay, if this is just doing complement stuff, I think that's what we need to do here because we don't have access to... We don't have access to anything else. I can't apply X. If I could apply X here, I could get the membership stuff. But I can't. So I think we need to start with some kind of compol. Okay, that's interesting. Yeah, I don't think I can apply that. Fine. Let's start with compol. I need to target something, don't I? AC. Or just A. No? Oh, at H? H1? Or they gave me an H1 and H2 here. They don't like this, though. Right, because I have to be... I have to actually target it. How about A union C? There we go. So if I target you, I can then rewrite you into this with compol union. So again, intersect. Doesn't do a whole lot for me though, I feel. You should know how to get started. Shoot. Okay, I need to go back. I have to go back. How do you prove that as a subset of another? To prove that A is a subset of B, you need to show that if some object X is an element of A, then it's also an element of B. Oh, they use intro. Okay, I was not thinking about this. I can break this down. Okay, well now I feel silly. So that's what I need to do. I need to do an intro. Ah, and then I can also do an intro on this guy. Okay, so I have more options than I thought. I can apply intro to this. To the goal. Yeah. Okay. What was intro H? Oh, right, because we have to... Because then we get a hypothetical. Right. Okay. We have an implication, and therefore we have to do that. Okay, well, I'm being stupid. So intro X. There we go. This should give us something to start with. So that means there's probably a way to break down H1 and H2, right? Because they are also subsets. Okay, here we go. Now you're giving me a hint. Now you use have to assert that X is an element of A union C. If you don't see right away how to justify this assertion, you have to write have HAC. Okay. And lean will set that as your immediate goal. Once you achieve that goal, lean will add that to your list of assumptions, and you can continue with the proof of your original goal. Okay. Oops. Okay, there we go. Now I can do this. X is an element of A union C. Well, if it's an element of A, then it's an element of A union C, right? So I just need to use mem union. Yeah. So how do I rewrite all this though? Also, can I do this on like a separate line? Or no? I guess it doesn't let me. Okay, so now I have this. It seems legit. I can apply that to this guy. Get a X is a union of this. No, is that not how that works? I just need to do this. Does that work? Yeah, it does. Cool. Okay, so my goal is still X as an element of B. If I have X as an element of B union C, that doesn't quite work out. So I probably need to process this side too, don't I? Like, I feel like I want to do another have AC, but with the and. They start with a union, though, for some reason. But, like, if X is an element of B union C, that means it could have just been in C, which means that we can't prove B. Or we can't prove this goal. We can't prove that it's in B from that alone. So I feel like I need to process this guy to get that. Right, we need to prove this. That A intersects C. So it's an A intersect C. We know that X is in A. We don't know that it's in C. But we need to prove that. We've proven that it's in B or C. How the hell do you expect me to prove this? I mean, I need this, don't I? So I can apply this. Like, I need to be able to get to here, I think. Because if I know that A is... Oh, sorry, if I know if X is in B and C, then I can prove that X is in B. So, like, I want to apply this, but I would need to prove that X is in both A and X is in C. But all I have are these unions, which seem kind of useless. I can rewrite them into ORs. Like X is a member of A or X is a member of B. That might just be what I need to do here. So I guess before we touch this, we probably want to break down these. I mean, I don't really see much else I can do. So do you have more stuff to say? No. No. I'm just gonna rewrite everything with memunion. Maybe it'll just make things a little bit easier to read. Yeah, wouldn't it be lovely if we could take this guy? I mean, yeah, we can R cases, right? We can R cases HBC. I guess I can't call it H1, H2. Let's call it HLHR. Yeah, so in this case, I can just do that. In this case, though, I just don't know what to do. No idea. So X is an element of B. I have to prove that somehow from this? Okay, but we have X as an element of C now. Ah, and then we can do this. Okay, there we go. This is where we needed to go to get that. I see. So now that I have XA and XC, I can turn those into a mem inter if, right? Because I have this. So I need to and intro. We're just gonna do like a have H A and C. We're gonna do an and dot intro on H HR. There we go. And then if we rewrite mem inter if, we'll have to do a reverse rewrite at HA and C. There we go. Now we can apply the other thing. So I can go H. What was it? This one. HAC. Yeah, have HAC2, I guess. I guess I should write out the goal. Or wait. Yeah, those are both the same. Never mind. What am I doing? What was it then? It was HBC2. Or well, let's call it HBC inter. I'm gonna use snake case for my variables. This one will be whatever the goal is here. And that'll just be H2 applied to... Oh, we have so many things now. You know what? Okay, so now we have that. We should just be able to take this and go... how do I take the left side? It was just exact HBC inter dot left, I think. Holy cow, we did it. And I completed combination world. Hey, there we go. Nice. GG's. Yeah, that was pretty tough. That was like a full hour. Actually, more than an hour to get that one done. Okay, so far, the elements of all of our sets have been objects in the universe U, but sets can contain other kinds of objects. In the next two worlds, we will work with sets whose elements are sets of objects from U. We'll call these families of sets from U. Huh? Elements of all sets have been objects in U. Sets whose elements are sets of objects from U. Okay, so these are sets of sets. We will call these families of sets from U. To indicate that F is a family of sets from U, we write F set of set. Okay, yeah. For example, suppose U contains the people in a certain club. Crying in the club. We want to form a committee consisting of 5 members of the club. The set of all possible committees is a family of sets from U. Each element of this family is a set containing 5 club members. Okay, I see. Families of sets are sets, and everything you've learned about sets applies to families of sets. For example, if you have FG, set U, and S set U, then mem inter if SFG is a proof of the statement S is an element of F intersect G, if and only if S is an element of F and S is an element of G. Okay, I think I understand. Mem union SFG is a proof of this, and mem compl if is a proof of this. S is an element of F complement if and only if F is not an element in F. So everything that applied to sets also applies to families of sets, kinda. Or so it would seem. In this world, we extend the idea of intersections to families of sets. If F is a family of sets from U, then the intersection of the family F is the set of all objects from U that belong to every element of F. Okay, interesting. Yeah, I guess that makes sense. In mathematical writing, the intersection of the family F is usually denoted big croquet goal F. In lean, the intersection of a family F is denoted intersect. Is that a 0? No, that's like a degrees sign, but like subscript. Like, I don't know. Intersect circle F. Oh, that's a 0? Okay, I mean, like, if you insist, that's a 0. Okay. I 0. Weird. That's not typing out the way I thought it would, though. Can you stop scrolling to the bottom? I just want to read, okay? Suppose we have F set of U and X U. Then X an element of the intersection of the family. Okay, so X is in the intersection of family F. Means that for every set T, if T is in F, then X is an element of T. To write this statement in lean, we write for all T is an element of F. Oh, if T is an element of F, then X is an element of T. Okay. Okay, let me close this. They probably gave me a bunch of new stuff. Oh yeah, they totally did. Okay, so we have for all now. Oh boy, lots of reading. Okay, let me finish reading the left thingy. Lean abbreviates the symbol as for all. Okay, for all T and F. Oh, comma X in T. Interesting. So these are syntactically equivalent. Gotcha. The symbol for all is called the universal quantifier. You enter it by using \for all. Note that for all T, if T is an element F, implies X element T means. Yeah? Okay. So. Okay, in other words, in terms of the universal quantifiers applying to the rest of the statement, if you want it to apply to less, you have to use parentheses to indicate that. Interesting. As with other set theory operations, we have a theorem that expresses this definition. Lean will recognize mem underscore s inter as a proof of any statement of the form x is an element of the intersection of family F if and only if for all T and F, X is in T. Okay. So that's what mem s inter is, and they give us that. So that one's a freebie. Lean will recognize mem s inter as a proof of any statement of the form X is an element of the intersection. Oh yeah, blah blah blah. You know. So the new things are U. Okay, so you're giving me some tips on like if it's a goal or if it's an assumption. Got it. So if Px represents a statement about an unspecified object X, then for all X, Px means for all X, Px is true. Okay. If your goal is for all X, Px, the tactic intro T will introduce a new object T into the proof and set the goal to be Pt. Be sure to use a variable T that is not already being used to stand for some object. Okay. Good to know. If you have an assumption of that form. Okay, yeah. So far we don't see any for alls here, but we're probably going to do some rewriting and they will show up. If A stands for some object, then HA is a proof of PA. Note that A must be the right type of object. For example, if X stands for an object in universe U, then A must have type U. If X stands for a set of objects in universe U, then A must have type set U. Got it. Okay. These are some object that HA is a proof of PA. My brain hurt. Okay, right. It's like a function, right? You can apply this guy to some object A, and then you'll get this. Yeah, and if it doesn't type check, then of course that's not going to work. Okay, so that's U, and this is just the intersection of the family of sets F. And this is how you type it. All right, sure. I guess since we start with a subset as our goal, I think the first thing we need to do is intro X. Because that was what we were doing before. And then we want to do an intro H. Okay, now you give me a new hint. Cool. As usual, you may find it helpful to use the rewrite tactic to write out the definition of X as an element of... I don't know what to call this thing. Intersection... family intersection? F? Yeah, I was thinking of using rewrite anyway. Okay, let's look at this. What's the direction on this? It's taking family to for all. Let's try and clear this world, and then maybe I'll stop for today. Remember the H. Okay, A for all T in F, X in T. Alright, is an abbreviation for that, yes. For all... Alright, right. Since this means for all, H can be applied to any set that we plug in. Applying it to set A, we can conclude that if A is an F, then X is an A. Right, okay, so yeah, this is a substitution. To apply H to A, we write H followed by A with a space between them. Thus, your next step can be have HA... Oh, how do you write the arrow? Is it like this? No. Oh, it's just imp for that. Okay. You can save yourself a little typing by writing have, right, it'll automatically infer. I don't really care. Since we also have H1 colon A in F, you can apply HA to H1 to prove that X is in A. This means that HA H1 is the proof of the goal. Okay, so exact HA H1, right? Or do I even need the exact? No, I do need the exact. Okay. The last two steps could have been combined in one step. In general, if you have H1, A and F, and H2 for all T in F, PT, where PT is some statement about T, then H2A is a proof of A an element of F, implies PA. And applying that proof to H1, we conclude that H2A H1 is proof of PA. Okay, so yeah, it associates to the left. For example, if you have H1, A and F, and H2 for all T and F, X and T, then H2A H1 is proof. Okay, isn't that literally what you just said though? Okay, whatever, I don't care. Moving on. In this level, we have two families of sets, F and G, with F is a subset of G. That means the intersection of family G is intersection of a family of sets that includes all sets in F. Plus perhaps more sets. Oh, okay, hold on. So F and G are families. So a subset operator works on families too. You're going to prove that intersecting this larger collection of sets leads to a smaller result. More precisely, you're going to prove that the intersection of G is a subset of the intersection of F. Of course, by now you know how to start a proof that one set is a subset of another. Yes, I know. And now you're gonna give me the show more help thing. Gotcha. So we need to rewrite mem s inter at h. Yes. So we have t in G, then we can we might need to rewrite U too. Okay, yeah, that gives us another hint. Now your goal starts with for all t. To prove it, you'll need to introduce a set t into the proof using a technique intro t. Ah. Recall that the set t is arbitrary. That is, t could stand for any set. So whatever we prove about t will be true for all sets. Okay. Intro t. Things are happening. Slowly but surely. You want me to do another intro? Okay, yeah, I can oblige, I guess. This is getting confusing. We have all these H's now. Okay, so yeah, we want to apply U to get to our goal. So you're the next issue. Yeah, so we know that T is in F. And because F is a subset of G, T is in G. Therefore, we should be able to apply this. Okay, I see the logic. I see where this is going. Now I just need to do what? Have HFG, where we take H1 and apply it to H2. Yes. Okay. Now you can combine H and HFG to reach the goal in one step. Exact HFG. Oops, did I do it wrong? Is that... Wait, what? Why is that not working? I'm applying... Yeah, I'm applying H, which is this guy, to this guy. Why does that not work? Shouldn't that work? Do I need to do another intermediate step? That's a sorry? Wait. What do you mean combine H and HFG to reach the goal in one step? I forgot how this works. I mean, I can do this, I guess. Oops, I need to exact that. There we go. That was a little awkward. You probably used intro several times in this proof. Recall that 2 intro steps in a row can be combined into 1 step. Click on intro in the list of tactics on the right for further details. You're actually absolutely right. I did kind of forget about that. Intro. Is there a way to comma them? If you're proving a statement with this form. Ah, here we go. Intro XH. I see. X space H. Okie dokie. So that's a faster way of doing that. This level shows that family intersections are a generalization of the intersections we studied in intersection world. You'll prove that if A and B are sets, then A intersect B is equal to the intersection of the family of sets that contains just A and B and nothing else. We'll need notation for the family of sets consisting of just A and B. We'll denote this family by curly braces A, comma B. And as usual, we'll need a theorem stating the definition of this notation. For any T, A, and B, member pair TAB is a proof of the statement T is an element of the family that consists of sets A and B. If and only if T equals A or T equals B. Okay, so T is a set, is what you're saying. Because to be an element of a family of sets, you have to be a set. So yeah, T is either A or T is B. Is equal to the intersection of the family of sets that contains just A and B and nothing else. Okay. So you want me to do like some hardcore rewriting. Mempair. Oh, okay. Here's an interesting little lore. If A denotes some object, then curly braces A denotes the set whose only element is A. Such a set is called a singleton set. Similarly, if A and B denote objects, then curly braces A, comma B denotes the set whose elements are A and B, and nothing else. Similar notation can be used to denote a set containing any finite list of objects. All of the objects in the list must have the same type. If the objects have type U, then the set has type set U. If there's another way to define sets. If Px is a statement about an unspecified object X, then okay, so curly brace X pipe Px denotes the set of all values of X that make Px come out as true. This is often called set builder notation. Okay, harkening back to like my first year comp sci years. It's the set of all values of X that makes Px come out true. Interesting. I'm sure we will see that soon. And then we have mempair here. I see. Okay, so this inter has priority over the curlies. So we probably want to rewrite. But the equals is even higher. Okay, if the equality is even higher on the list, then we might want to X. And then in this case, we need to use constructor. And then we can do intro H, I guess. There we go. Good start, I do believe. Now we can do a rewrite on U with mem as enter. Yeah, looks good. And then do we need to do another rewrite here? Because yeah, we have something of this form. We could turn it into an OR. I think that's what I would like to do. Let me go do that. Mem pair. So rewrite mem pair. No? Okay, doesn't like that. Interesting. So that's not how that works. Huh. Why? Is it because of this? Is it because of the for all? Why is that? Eh? Eh? Oh, do I need to intro first? Hold on. Okay, let's do another set of intros. Okay, that's weird. Oh wait, no. This is of the right form now. Okay, here we go. Now I can rewrite mem pair, but this time it's on H1. Okay, I see. Oh, this is tricky. Okay, starting to get a better picture of all this. So X is an element of Y. Okay, well we have this. That seems pretty cut and dried. We can break U down. Because, yeah, we have Y equals A or Y equals B. So we can, our case is H1. And now we have a rewrite rule for this. Probably need to do this direction. Yeah, there we go. And now if we do... Hey, there we go. That works. And then we just do the same thing here, right? We do a rewrite, reverse on R, I think. H, what's going on? What happened here? Yeah, what doesn't like that, so I do this. Yeah. I don't know why it was giving me those error messages. Whatever, I guess it was kind of bugging out. And then we just go exact h dot right. And now we have to do this side. Okay, so this should be pretty simple. Control H, and then we have our goal looking something like that. We might want to break down that goal, but I think we can probably leave it actually. I don't think we need to. What I'm going to do first is rewrite at H. So we're going to take a rewrite here, apply, what was it called? Mem S enter at H. And that will rewrite that into a for all. Now we can do our double intro. So if we intro what? Oh, we already have an X. So we're going to go intro Y and then intro H. H1. Oh, does it not like Y? Is it because I already used Y earlier? Oh, because that's in my hypotheses. Okay, that's a little bit different. Okay. That's in my hypotheses. Ooh. You're in my hypotheses. So who's messaging me? Oh, a bot. Never mind. Let us ignore that. Huh, I wonder where that bot came from. We'll check that later. I can't rewrite here. I can't use intro here either. I can't go like intro at. Is there something I can do with mempair here? Or actually, let's look at for all. For all probably tells me what I can do. If my assumption is a for all, then I can apply it to something. But it needs to be the right type of object. Well, okay. I could have... Ooh, I don't know. I'm just gonna call it I for now. I don't have a good name. We'll set it to H applied to X, because I think X is right, no? No, I don't think that's right. But T is a set. Oh. So I could apply it to like A? Oh, this is weird. Yeah, I guess I could just do that, huh? Let's call it XA. I think that's a better name. So X is in A. Oh, HXA. Oh, that's still an implication. But now I should be able to rewrite it? Must be missing something here. Mempair. HXA. Did I need to do this halve? I'm wondering if I needed this at all. How do I comment this out? Like this? Haskell style? No, it doesn't like that. So I did need to do this. And that gives us an OR. I'm starting to wonder, like, what the hell is happening? Oh shoot, I already did this. Does that not work? Oh, this is... Oh, that's below... Oh, okay, that's below that. I didn't realize that this was above. So I need to do another intro here? No, I can't intro, right? It's a hypothesis. I mean, I can prove A equals A. No. It's not that. So I have X as an element of A now. Wow, this is... This feels like I'm breaking this down into like way too many steps, but at the same time, I mean, it's working, so like, it's not bad. I don't feel like it's bad if it's whatever works, right? You take what you can get. So just do this, but again. Rewrite mem pair, yeah. And then instead we do have xb is hxb on the right side. Yes, that looks better. So we have x is in A and x is in B. And because x is in A and x is in B, we can just do an and exact and dot intro xa xb. There we go. That was weird. That felt more complicated than it needed to be, maybe, or like I feel like I overcomplicated it, but I mean it worked. So like, is that bad? Like, I don't know. Maybe that was the way to do it, though. If F and G are families of sets, what is intersection of F union G? In this level, you'll find out. Whoa. Stay tuned. Okay, so we have an equality. I'm gonna do an x right away. As my opening move into constructor. No, excuse me. Intro H. We want mem s enter, right? No, does that not work? Oh, because of this union. I guess I could apply it like that. No. Oh, because you're right. Because this. Oh, sorry. This intersect is in the way. Oh yeah, the difficulty definitely went up after the tutorial bits. Oh boy. We can rewrite at the H. Let's do that. Okay, so now we have this. So I should be able to apply H to F, right? Or not F, X? No. Wait. Right, because it has to be, X is not a set, I just realized. But F and G are both families. Yeah, there are layers to this proof. I see. I want to break down these somehow. But all we have is like, we have like this. And we have this. And obviously this one's important. But the problem is this union. Or sorry, this intersection. I don't know if this matters. Because like I can do that. Oh, it does matter because now I can rewrite that using the thing that I just got, right? The mem s enter. Because otherwise I can't do that. Okay, I see. There we go. Okay, now things are happening. So we have two of these for alls. Okay, I see how this would work, kind of. Like, so if T is, like, for all sets T, if T is in the union of families F and G, then X is an element of set T. Like, that makes sense. So if it's, so basically T needs to be in either F or G. And then we have, for our goal, T, yeah, for all T in F, X is in T, and for all T in G, X is in T. Right, and we have this thing. We know that if it's in either of them, then it'll end up in X, or end up in T. So that's, I see the logic. Okay, and that can let me break down my goals. That looks kind of good. How do I rewrite this as... Can I, like, shrink this? Okay, yeah, so now everything is starting to come together. So I can rewrite mem union at H. No? Is that not? Oh, it's because you are not a set. You are a set of set, right? Wait, shouldn't that also work? Yeah, that should still work. Or at least I thought it would. Oh no, because the membership, right, it doesn't apply. Oh, okay. No. Oh, what if I intro here? Intro Y. And H1. Oh, here's an approach you might try. If only you had HFG, Y and F union G, then HY HFG would prove the goal. Okay, so yeah, I had to unlock Y for this hint to appear. So wait, if I just leave it at this... Oh no, I need H1 as well. Okay, so this is the new hint. Interesting. Oh my god. Use the tactic apply HY. Lean will figure out that HY could be applied to a proof of Y. No, Y and F union G to prove the goal. And it will therefore set Y and FG as your goal. Holy moly. Hello, fellow not leaner, assuming the law of excluded middle. You're occupied with solving a Sudoku with a friend and forgot about this stream. Ooh, was Sudoku fun? I've never done co-op Sudoku before. That sounds interesting. My brain hurt. What? I mean, I thought I was going on the right track. I could like kind of see where this was going. But then they threw this at me and I'm just like, huh? So use a tactic, apply HY. Lean will figure out that HY could be applied to a proof of Y in F union G. I'm trying to figure out why that would work. Like, why would the apply HY... They don't figure out that HY could be applied to a proof of Y in F union G. And how does that help me? It was this big Sudoku called Sudoku-vania. Oh. We managed to solve one of the boss sports, and it took 2 hours? And that was just the first section. I feel like I'm cooked. Oh, jeez. That sounds like a lot. How does this help me? I know I have this. Yeah, I guess I can just or dot in L H1. Gosh. Well. Wait, and then... And they don't even ask me to do this on this one. It's just... I don't know, so I don't even have to put the Y in. It just figures it out. Okay. Okay, now we're getting into sorcery. It just changes the goal so it's easier to think about. I'm just not sure how it applied. Because, okay, so the goal was X is in Y. And we're applying H, apparently? Oh, so it's replacing T with Y. Right, because this would be like the goal of this implication, if I'm to read this as an implication. And so like this unifies with like this thing. And then it becomes, okay, and then the new goal becomes Y is in F union G. Okay, I see. Wow, that is very mind-bending. It just does some pattern matching. It's just going in reverse. So think of the last step. If H had a Y in place of T, then it would imply the goal. Yeah, okay. That's that's pretty much my conclusion as well. I don't know why you have to be explicit with the Y here though. Like, why do they do that when you can just go apply H, and it just like magics into place? Okay, so this guy is at the top level. Mm-hmm. Oh, okay. And now I need to drink water. Okay, there we go. No, we need to do this. We need to be right with this. All right, now this is up here. Which means what exactly? I think I can break that down. But I can also do some intros here. Let's just do the intros. Okay. And now I can apply... No, I can't. But I want to extract you. You're in the way. This intersect is in the way. Mm-hmm. Okay, there we go. Now I can rewrite both of you. Yeah. Here we go. And then I should be able to do... So wait, why is a set? T is also a set because F and G are families. So now I can R cases H1. And then I can apply H to L. Right? No? Why doesn't it like it? Okay, let me not skip steps. Does that not apply? Oh, right, because H is an and. I need to H dot left L. Don't I? Why did this become a sorry? What did I do? Is L not the right form? Because y is an f. So why couldn't I apply... Did somewhat struggle with the latter parts of set theory game. Yeah, it is getting a little bit trickier. But this kind of feels like the mid game. I mean, that worked. That worked. We take those. We take those. Last goal. Okay. Let's do this. I like how I ran out of names. I don't have good ideas for names. I'm just calling this thing A. And then we apply A. And then we exact R. And then we win. Okay. I don't know, man. This is definitely not like the sexiest proof. But I think you put Y then L? I don't know. Well, I did it with apply. Oh boy. If A is a set and F is a family of sets, under what circumstances is it the case that A is a subset of the intersection of F? In this level, you'll discover the answer to that question. Okay. Jeez. Mercy. Okay, so there's an if and only if here. Right, and I can examine the structure here. So the syntax tree starts there. It's the root node. So I should be able to just constructor. Oh boy. By the way, I managed to get a 3-line solution without semicolon for the last level you solved last stream. Really? What did I do on that one? That was Union World, right? This guy? You did this in 3 lines? I did it in 32. You did this in 3? Four. Okay. That's crazy. You must have taken a shortcut, right? Like, you must have used, like... What did you do? Did you use compl? Oh, combination world 1. Oh. Right. I forgot I actually finished 1 before this. Oh, this one. Okay, so I did this in 22. You did this in 4. You must have used, like, compl, right? There's more than one way to do the proof in this level. I have a feeling let's use whatever you did here was probably compl related. Compl shenanigans. Okay, so this is an implication, so we need to intro. Sure. We could do more intros here. Let's call this one HF, whatever. Or HXF. I don't know. I feel like that's a better name. And then we can rewrite this guy. Mem as inter. So okay, what do you do? X rewrite mem compl if mem inter if mem compl if mem compl if mem union push neg breathful. Oh, so you just like stuck all those transformations into this one rewrite list. I see. That is significantly simpler though. Very nice. So I want to do rewrite mem s inter. Yeah. At h. Yeah. No. It doesn't like that. Oh wait, no, because that's not. I forgot that's a subset. Wait, how do I deal with you then? Actually, my goal is a subset. Should I break that down? Oh my god. Yeah, I can take this like all the way. But I don't know if I want to do this. Like, is this... Am I insane for doing all this? This is like a lot of extra work. This thing, I feel like... There's a way to break this down, right? Like, can I turn this into, like, membership somehow? It feels like I should be able to do that, because I want to get rid of this. And the only way to do that is through membership, so, like... Whatever. Yeah, there we go. Then I can rewrite mem s inter I. Sure. Then I have this. Then I can apply. And then we can exact HXF. All right, well, that worked. It works. You like breaking stuff down? Okay. It's a function from a membership statement to another membership, yeah. I figured it out. I did it. I used my brain. Notice that the parentheses in the next goal are necessary to indicate that the universal quantifier applies only to the subset statement. Without the parentheses, Lean would interpret the universal quantifier as applying to the rest of the statement. Okay, so that's just like a whatever. Oh, wow. Stop. Oh, do I want to do this? Oops, no apply. Intro. You know what? I'll take your suggestion. T. Oh, wait, no, T is already used. What did we have before? I have too many variables. One time you named everything H1, 2, 3, 4, 5. Yeah, I feel like this is like the hardest part of Lean. It's just like, how the hell do I name everything in a way that makes sense? Like, it's like, I want my proof to be like readable, but at the same time, it's just like, here's all the variables in the world. Name them all. It's like, name your 12 children. Oh, T wasn't used? Okay. Well, see, my brain is just confused by like literally everything. You know, fine. You can be T. Okay, so now I have to work with H. This applies, right? Or not? Well, I see I have T and F. And I have this for all. How do I do that? The thing is, I want to treat it as like it's just a function, right? So. Oh, it's this. There we go. Now I understand. Okay, just read the documentation. It's so easy, forehead. There we go. Okay, well, I got in 12, at least. Level complete. Yeesh. These are getting kind of ugly. In this level, you'll need a new kind of proof by cases. For any statement P, the tactic by cases HP will break the proof into two cases. What? In the first case, a new assumption HP is added to the list of assumptions. In the second, the new assumption H not P is added. Since P must be either true or false, these two cases cover all possibilities. What? What does that mean? By cases. Ugh. So it assumes not P? Wait, I'm so confused. What do you want me to do? My case is H? But there's no H. Okay, maybe we don't buy cases yet? Okay, let me just break it down the usual style, and we'll see where by cases kicks in. They just assume the law of excluded middle, yeah. I see that. If I have some statement A equals 2, and that statement is H, then by cases H would split your goal into 2. One where you assume that A equals 2, and one where I assume that A is not equal to 2. At least that's what I would assume, right? Like, to me, that makes sense. I'm very confused. Like, do I do it right off the rip, or do I wait? I'm gonna just go for what do I do if this isn't my goal again? Right, I have to intro. They were like intro Xing earlier, so I'm gonna intro X. Intro X H, sure. Writing out the meaning of the goal will make the proof easier to understand. Okay, so they're telling me I need to like do stuff first, right? So like break it down. Yeah, I have a feeling it's gonna teach me. So like right now, you can do by cases H colon A in A or something, and it will split the goal into two. my brain, my brain does not like it. Okay, can I? Let me just break it down because I'm like I feel like it'll become clear when I actually understand what the hell's happening. When they'll prompt me, I'm sure, right? Okay, so now, yeah. So this is what our goal looks like. It's an or. If x is in A, then the goal is easy to prove. This suggests breaking the proof into cases depending on whether or not x is in A. You can do this with the tactic by cases HA, x in A. All right. And I need to give it x in A. Oh, interesting. So I have to annotate it. So my goal didn't change. It just added another goal. Except, how come my further goal looks exactly identical? No, yeah. Why are both of these goals the same? That's weird. Oh, because the hypotheses are going to be different for this one. Right. Oh my god. So you're adding a brand new assumption. So you have to give it a type. First case is the easy one. I just find it so weird. Like, how would you like know to use by cases though? Like they told me here to invoke the power of by cases, but like I feel like in general it's not really obvious. So let's say you want to prove that x is in A or not x is in A. This is obviously true by the law of excluded middle. Yes. Because either it's in A or it's not in A, so like that makes sense. You can prove that without any assumptions. So wait, so when I did by cases, that basically was invoking the law of excluded middle. Because that's basically just saying like, yeah, I want to assume that it is that x is in A, and then prove the goal, and then assume that x is not in A, and then prove the same goal. But in order to get those two new assumptions, I have to buy cases, so yeah, like if there was no law of excluded middle, then I couldn't do this. Oh, so if I need to appeal to the law of excluded middle, then I would buy cases. Interesting. For the second case, which half of the goal do you think you should try to prove? You can use apply or.inl or apply or.inner. Probably or.inr, right? Well, the equivalent tax left and right will prove. This is how you're going to prove. Well, I definitely can't prove left because we know that x is not an a, so we're going right. We're turning this car around and we're going right. And now I need to use mem center. Okay. Looking good so far, kind of. Okay, so now things get complicated again, yeah? For all t and f, x and t. Does that help? You just call that t and ht? The two new introed things. Oh, you mean when I do this? Okay, so now I can apply h1 to ht. No? But why? Isn't h... because ht is an f. No, it's t, sorry. Yeah, there we go. And then I can give... Oh. Something like that. I don't know, man. Names. There's too many of them. And it's all... I don't think I need to like have all this stuff. I'm just making things harder for myself, aren't I? I mean, like, I could just do this. A union T is in G. Okay, at some point we need to use H A. So A X is not an A. My God. My head hurts. Because we know that A is either... So, yeah, it's either... So, A union T is in G. We know that X is not an A, though. Oh, hold on. I see. So I apply this guy to this guy. You know what? I don't know anymore. So I would do H, and then no, stop. There we go. Okay, so now we have this. And because we know that this guy is not an A, we should be able to prove that X is in T. I feel like I'm so close. How do I use membership again? Or like anti-membership? I guess it's just a negation, right? It's just a function. If you're just a function, then I need to do... Need to do what exactly? Wait, do I want to R cases this? Yes. Okay, yes. I want to R cases HATG with left and right. Because now I can feed HA to this L. Because if we know X is an A and X is not an A, I should get like a void. Yeah, and from false I can prove anything. No, does that not work? How does this work? The goal isn't false yet. But I should be able to prove anything from this, right? You can guess cases on false and win. There are cases. Hold on. I need to see that. I need to see that. Okay, so I had false. I did a cases on false. I mean, and they gave me R. Oh no, R is from up here. Wait, what? So this L2 and R2 didn't even do anything. Whoa, what? Oh, I don't need the width? I was like, yeah, because that seems like really weird. Oh, it does just work. False is considered 0 cases, so it is vacuously true. That is crazy. I never would have thought to do R cases on B, though. Okay, I guess, like, yeah, if I have false in my hypotheses, or in my stuff that I have proven, my objects, and my goal is anything else, then I guess I can just R cases it, and then it'll just go away. Show more help. You have contradictory assumptions. Can you prove anything from contradictory assumptions? Oh, they wanted me to use by contra. Oh. Oh. I was like, this is weird. This feels very bootleg. Okay, that's why. They wanted me to use by contra. How would that work? Since the goal is a false. And then I could probably do like some kind of double negation, I guess. Or double negation elimination. Okay. And that would have given me the false goal. Interesting. But this was cooler. It wasn't. It was more interesting. I feel like I learned something new from this. Okay, I have 10 minutes left. Let's peek at Family Union World. Is the first one going to be super hard? If F is the family of sets from U, then the union of F is a set of all objects from U that belong to at least one element of F. We'll investigate unions of families in this world. Okay, yeah, that's kind of what I figured. Is this going to be hard? It's 1 out of 7. Jeez. To work with unions of families, we'll need to know how to work with existential statements. If P X is a statement about an unspecified object X, then there exists X. PX means there is at least one X such that PX is true. The symbol there exists is called existential quantifier. You can enter it in lean by typing \exists. The easiest way to prove the statement there exists x, px, is to specify a value of x and give a proof of px for that value of x. The theorem that allows you to do this is called exists.intro. If you have HPA for some object A, then exists.intro AH is a proof of the statement exists x, px. The object A is sometimes called a witness for the existential statement. In this level, you'll try out this theorem. Specify a value of x, give a proof of px. For that value of x. Right, so it's like a pair. So you give, you specify a value of x and give a proof of px for that value. And you need to use exist.intro for that. So if you have HPA for some object A, exists intro A and then H is a proof of that. So you're pairing A with H because H has type PA. The object A is sometimes called the witness. A witness? The witness? Funny the witness reference. Your goal says that there is a set that is a subset of A. Okay. The theorem subset.ref will suggest such a set. Oh boy, so we have U. If px represents a statement about x, then there's x. Px means there is at least one x such that px is true. To enter the symbol, yeah. Yep, okay, that's exactly what they said. Close the goal. If you think PA is true, but you don't yet have a proof of it, then apply exists.intro A will set PA as your goal. The tactic use A does the same thing. Oh, right, use. I feel like I haven't seen that in like ages. I forgot what that even was. But it also tries to prove PA. If it doesn't succeed, then it leaves PA as a goal for you to prove. We have an assumption H. There exists XPX. Obtain. Okay, that's new. Oh, you get these little funny, like these funny brackets. I feel like I've seen those before in like my physics class. The one, the one where my professor abandoned me to get the milk. Okay, so this is a new object W and new assumption HW into the proof into angle brackets. Oh. Okay. Interesting. I should click on a circle and draw a line. Yeah, you're right. That is click on a circle and draw a line, the game. Okay, and here's exist.intro. If x represents a statement about x and you have HPA for some object A, then exist.intro AH is a proof of there exists XPX. Yes. Is that all we got? What is subset.refl? That's this guy, right? We already have this guy, though. Okay, so does that mean I just need to exist.intro ruffle and subset dot ruffle? Oh, I need a tactic, don't I? No, this doesn't work. No. Well, I have an A. I have an A. Why like this? The subset.ref will take something? Ah. There we go. There we go. I personally prefer using use for existential statements instead of trying to do it as a one-liner. Oh. Well, what would that look like? By the way, another set that would have worked as a witness for the existential goal in this theorem is the empty set. What? Denoted as this thingy that you can't type. However, to justify the use of that witness, you would have had to prove that the empty set is a subset of A. Since we already have the theorem subset.refl, it was easier to just use A. Now that you know how to prove essential statements, you're ready to start working with unions of families. So what if I did it with use? What would that look like? This is just, what is it? Use A, use H? I don't remember how use works. I'm not gonna lie. I kind of forgot. Use A does the same thing. But then it errors. Okay, anyway. Maybe we'll figure this out another time. Oh, I don't have use unlocked yet. That's why. Ah, so you're trying to tell me to do stuff, but I don't have it yet. Oh yeah, it's here. I have to unlock it first. No. We gotta do the one-liner first, okay? And then we can start using stuff. Okay, I'm gonna leave it here for today. I gotta get going. We made some good progress. I hope we can beat the rest of this next stream. I don't know if we can. It might take 2. Because yeah, it looks like things get harder and even longer. I might just start stream earlier next week. We'll see. Hopefully I'll be able to stream next week. And I don't run into my deadlines too hard. But that's gonna do it for today. So thank you all for watching, and we will continue to play set theory game, hopefully finishing it off next stream, so we can resume playing Star Force the week after. All right, goodbye. See you later.